Hey, this is Horner, and this is the 2016 AP Physics C Mechanics free response question. It is number 2, and we have a block of mass 2m, so there it is. It is on a horizontal, frictionless table, and it is attached to a relaxed spring. So we know that this spring is relaxed, and so as soon as I can pick up the pen, there we go, it is relaxed. So it's not compressed, it is not extended. The spring is non-linear and it exerts a force of negative bx3 where b is a positive constant and x is the displacement from the equilibrium of the spring. So for this spring, if you were to plot what was going on and you wanted to plot force versus stretch, it is not going to give you a straight line. It will give you a cubic curve. So that's what you have to remember for this one. A block of mass 3m and an initial speed of v0 is moving to the left as shown. So there it is. On the dots below, which represent the blocks of mass 2m and 3m, draw and label the forces, not the components that act on each force before they collide. Each force must be represented by distinct arrows starting on and pointing away from the appropriate dot. So that's just really important for you to always remember to do. For this one, we're going to start at the dot. Oops, and that's really curvy. So you don't want to do that. Make sure that all of your lines, you use a ruler, and you'd want to try to get them as straight as humanly possible. I can't use a ruler with this program, so we're just going to do it this way. This is 2mg, because it is 2m, and then this one is going to be 3mg. On this test, they won't ask you, like on the AP Physics 1 test, they'd have lines, and you'd have to make sure that they're the right size, but these you really don't. You do need to make sure that these are equal and opposite, so we're going to make it a little bit longer there. We'll put a little arrow there, and then we'll just kind of do the same thing here. So those are the same size, and then these two are the same size, because these are the force normal, so this is Fn1, and this one would be Fn2, and then here we have 3mg. So now we are all done, and there are 2 points for that. For the next part, it says the two blocks collide and stick to each other, so there we go. Right off the bat, I would just write inelastic, and at this point, you probably should also write K initial is not equal to K final, because you don't conserve energy here, but you will conserve momentum. So that's an important point. Derive an expression for the speed of the blocks, after the collision. So we can't do this with energy, but we can do it with momentum. So for letter B, we'll just put B right here. The thing that we want to do is just say that the momentum at point 1 or before is equal to the momentum after. Momentum before would be 3 times mvo for our original speed, and that's equal to then 3m plus 2m times vf, because the two are now 1 and have one final speed. At this point, we need to go ahead and combine everything, so we're going to divide both sides for the by 3m plus 2m, and so that would be 5m, so we're going to do 3 over 5 times m times VO is equal to m, let's see, 3, whoops, nope, that'll just be equal to VF, oops, and this is over 5m, sorry, and then that is equal to VF. So let's get rid of this guy right here, and we know that that's equal to VF. So here we go. So there's VF. Notice that the m's cross off, so your final answer here is VF is equal to 3/5. Wow, that's really bad. 3/5 VO. All right, so we're done with that part. Next part says determine expression for the kinetic energy of the two-block system immediately after the collisions. So we need to do that next. Let's go ahead and find the kinetic energy after. So kinetic energy after, this is letter C. we know is k is equal to 1/2 mv squared. They just want it after, so here we're going to do kinetic energy is equal to 1/2. Remember we said that the total mass is 5m, or 3m plus 2m, and then our final velocity here is 3/5 VO, so this would be 3/5 times VO squared, and then we need to make sure that we go ahead and multiply everything through that we can, and so here you're going to end up with k is equal to 9/10 mVO squared. So that is your kinetic energy. Letter D wants us to derive an expression for the maximum distance d that the spring is compressed. So to do that, we actually need to move on down here and go on to this blank page that I have. Best thing to do at this point, I got to turn this pin thing back on because it turned off, is to do the following. Here we go. We know that the change in the kinetic energy of the system plus the change in potential energy of the system, that should all be equal to 0. And if that's true, that our original kinetic energy should be equal to the potential energy final. Kinetic energy original is going to be what we have here. So this is 9/10 times mv original squared. And then that is equal to, so remember the potential energy final here, we know that the force is negative bx cubed, and if I want energy, remember energy is equal to work. So change in energy is equal to work, and work is equal to the integral of f dx. And because of that, we know what the force is. We're going to do the following. We know that you've got to do this from a position of x1 all the way out to x2, and we need to integrate that equation that they gave us earlier. So earlier they told us that this is negative bx cubed, that is the fx. So if fx is negative bx cubed, we need to put in negative bx cubed dx, and this also needs to be negative. And we know that this is negative because of the way that the spring is compressed. So negative force from that spring going away from its equilibrium point. Okay, so now that we've done that, let's go ahead and do our math. So we'll have 9/10 of mVO squared is equal to, so we're going to take negative times negative, that makes it positive, so this is x1 to x2 times bx cubed times dx. And we want to go from 0 to d. So remember, in the original part of the problem, we're going from 0 to d. So this is our x1, this is our x2. So this is x1, and this is x2. And so we're going to use the notation they have there. So let's go ahead and say 9/10 mVO squared is equal to the definite integral that goes from 0 to d, and we'll do bx cubed dx. And now we can actually do the actual integration. So this is 9/10 of mVO squared is equal to, and then we have our quantity bx. Remember, this is, we're going to use the power rule, so 3 plus 1 is 4, and we're going to divide that by the same number 4, and we know we've got to do that from 0 to d. And that makes it really nice because now we have 9/10 mVO squared is equal to, and then this is going to be, remember we're going to put in 0 first, we'll put in d first for our variable, and then we'll put in 0. So this is going to be b So here is our B. B times D to the fourth over 4. Okay? And they want us now to make sure that we solve for D. So this would be minus 0 because of our 0 down on the bottom. So let's solve for the D. To solve for the D, we need to multiply both sides times 4. So that would be 4 times 9, 9 times 4 would be 36. And then we're going to have that over 10. And we have, now we have m times VO squared, and that is going to be over, and then B has to be divided by the other side, so this is B. Sorry about that. And then that is equal to D to the fourth. So now at this point we can reduce this down. This would be 18 over 5. So now our D is equal to, and we're going to do the fourth root, because this is D to the fourth, we can do the fourth root on the other side. And we can put 18, because 18 times 2 is 36, and then 5 times 2 is 10, so that would be the 5. And then we leave our MVO squared on the top, and on the bottom we still have our B. And that is our expression for D. Just lots of weird math there. Where does the points, or where do you get the points for this? So one of the points comes from saying that the correct expression for the conservation of energy. So that would be really, if you just had this, you'd be fine. The next thing you have to do is attempt to integrate. So even if this isn't right, as long as you showed that you're trying to integrate it, let's say you don't have the negatives here, you just have this and you skip to that step, that would be okay. For the next one, you've got to go in and put the correct limits of integration. So we're going from 0 to D. And then for an answer that is consistent, so if we move this guy down and come down here and you get your final answer, so oops, it's not wanting to stop. There we go. Oh, no. There we go. So then this part right here, your final answer is going to be a point. So that's where those points come from. For the next part, it says, in which direction is the net force, if any, on the block of mass 2m when the spring is at maximum compression? So the answer that you want here is it is actually to the right. It is actually to the right. So we're looking at the force on 2m. So when it's completely compressed, the force on 2m coming from the spring is pointing towards the right on 2m. So we need to say that there's a maximum compression. The block of mass 2m has an acceleration to the right because all those forces are acting on that 2m mass, and the acceleration is going to the right. So that's a pretty easy thing to see, that it is going to the right. So when it's compressed, basically you could say at maximum compression the two-block system is instantaneously at rest, so the only horizontal external force is due to the spring. So here we just put only F, and then you could external force is from spring, and it is to the right, so it's acting on that block. For part double I, in this one, they want to know which of the following correctly describes the magnitude of the net force on each of the two blocks when the spring is at maximum compression. And so here, if you look, the magnitude of the net force is greater on block of mass 2m, it's greater on block 3m. The magnitude is on each block has the same non-zero value, or the magnitude of the net force is 0. So for this one, the magnitude of the net force is greater on block of mass 3m. So the question is, why is that? So both blocks have the same acceleration. So both blocks have the same acceleration. Because they are together, they do have the same acceleration, but block 3m has more mass. So block 3m has a greater mass, and so therefore it should have more force acting on it. So the net force on it must be greater than it is on block 2. Because remember, F is equal to 3m times A, and that is going to be greater than F is equal to 2m times A. So that should help it make a little bit more sense. And then for the very last part of this problem, it says, do the two blocks which remain stuck together and attached to the spring exhibit simple harmonic motion after the collision? And the answer here is going to be no. And so really what we need to do is, because it is not a linear spring, okay, simple harmonic motion is the resulting motion of a linear force. So here you basically just need to say simple harmonic motion results from a linear force, F-O-R-C-E, and this spring does not behave in a linear fashion. And so that is the important part for this one, and that is the end of this problem.